describing radiation heat transfer. That's why I'm going to take a little bit longer with this. And then I will talk about the governing equation and boundary conditions for this specific device, and a little bit of the mathematics of the strategy of solution of this for this big model. And then I will talk a little bit about the results, meaning the way we understand the device. First of all, I'm going to simplify the model in such a way that we can understand the big properties of the working of this kind of devices. And then I will dive into the solution of the full model, the big model, and try to see whether we can describe it in detail the small features that make a good or bad design for this specific purposes. And then I will end up with final remarks. Okay, first of all, I want to justify the efforts that we're putting on this topic. As you well know, solar energy is plentiful and viable alternative energy in Mexico. This is a map of the solar energy radiation, the density of the solar energy in our country. And as you can see, red is the highest. As you can see, there's a lot of solar energy in Mexico. So it's worth taking a look at what's the possibility of using this source of energy. This is a map of direct solar irradiance, and in the northwest states, and even here somewhere in the center of Mexico, we have 2,500 kilowatt hour per square meter per year. That's a good news. That's very good. Let's try to see whether we can somehow harvest this energy resource. But we know that solar energy is, first of all, intermittent. We don't have solar energy at night, obviously, and it is diluted. We have only 1 kilowatt per square meter. So, if you think of solar energy, you can see that, fair enough, it has very good properties, but it has some other properties that make the usage of solar energy a little bit difficult, to say the least. So, what has people proposed to improve the usefulness of solar energy? Well, for instance, one of them, there are very many, but I'm just going to talk about one of them. Solar energy concentration solves many problems of naturally occurring solar energy and opens up a large variety of potential applications. For instance, and this is what I'm going to focus in today, with the concentration we have high density energy. And another feature is that potentially we can make an efficient storage of the energy. So even though concentration implies some difficult technological challenges, nevertheless, it solves some of the key problems of solar energy. In particular, we can make high density energy. Okay, let me tell you that in Mexico we don't have big concentrators like this one. I think this one is in the US. But we are trying to, in my institute, we are trying to develop technologies to understand or at least be familiar with some of the technological problems of these kind of systems. What people have done is they have built solar furnaces. What do we mean by solar furnaces? Essentially, big mirrors that concentrate not not as the concentration is not as large as in the picture before, but they do concentrate solar energy somewhere at certain point. The largest solar furnace that has been built is in France, and I'll give you some numbers so that you can start having some scales in your minds. This solar energy concentrator has a factor of 1,000 suns. That is, do I have to put it higher? Lower. Right. I hope this works better. Is it? Is it better? No. Or I can use this perhaps. Is this? I think this is better, isn't it? Okay. So with this furnace, we have 1,000 suns, and there's a 1,830 square meters a parabolic concentrator, as you can see in here, and in front of it we cannot see because it's the picture was taken from this this direction. There are 62 heliostats with a total area of about 3,000 square meters. And now the spot is 80 centimeters in diameter. So it would be something like so. Okay? So this is the largest solar energy concentrator. And in Mexico, we do have a solar energy concentrator, a solar energy furnace, which is in our institute. And I would like to quote the same properties that I was referring to in the previous slide. We have a concentrator factor of 18,000 suns, that is almost twice as large as in the French one. There are a little bit more than 400 hexagonal mirrors of 42 square meters, which are inside this building. You can barely see them in here. There's a kind of a blurred image of the concentrator. We have just one heliostat with 81 square meters, and the spot that is formed is only 7 centimeters in diameter. So it's around this big. So even though in France the concentrator is bigger, also the spot is bigger. And in Mexico, what we have is a smaller spot, more energy concentrated. It's not a point, obviously. It's a circle, but the amount of energy that is concentrated in there is huge. So, as I said, this is the heliostat. The sun is going up here. It shines and hits the mirror. The mirror sends the beam to this building, and in the building there's a parabolic concentrator, and also the center or the focus of the parabola is inside the building. Here I can I'm trying to show you the optics. Essentially, these straight lines represent the beam that come from the heliostat, and then they hit the parabola and they concentrate in a central spot, which is in here. This is an actual picture of the spot that is the light spot that is formed at the focus. And in here, there's an effort to visualize the solar beam. The sun comes from here, the radiation comes from here, and my colleagues that work in this device put a little bit of smoke so that the radiation could be seen, could be visualized, and this is the focus of the spot. So this is not a very good visualization, but gives you the idea that we have kind of a cone that is concentrated at certain spot. This is what would be equivalent to this position here. Okay, so we have now the a lot of solar radiation in this at this point, and what we normally do, or what people that work in this field normally do, is that they design heat exchangers ad hoc for this purpose. We do have a lot of energy at this spot. The point is, okay, now what would we do with the radiation? What can we? How can we convert this very much concentrated energy into useful energy? So people started thinking on heat exchangers. Okay, now just think a little bit about this problem. Imagine that you were facing this this problem, and you were told to design a heat exchanger for this purpose. What would you do? If you take a standard heat exchanger, a normal heat exchanger, what we were not normally told in our classes in heat transfer is that we expose certain surface to the incoming radiation, or to the hot source, and see that somehow the energy heat would transfer through the wall and then go to the working fluid. Those are the kind of basic ideas when we design a heat exchanger. Now, if we do this at this point, if we put a standard design heat exchanger in this spot, what we would be getting is that the exposed surface would heat so much that, well, first of all, it will start re-radiating energy back to the system, which would be lost. Then, in very many cases, if we're not careful, we will the system will be melt by just the sheer fact that it is exposed to a very high radiation field. So what we proposed, we thought it was an original idea, and then we discovered that very many people have thought about this before. But well, anyway, it's a little bit frustrating, but understandable. What people have done is that they use not a standard a design heat exchanger, but some kind of cavity, some kind of a container. And this would be the usual design. We have in front not a surface but a window. And then the radiation comes in and hits something that is inside the container. And the working fluid that should be in here would be something that absorbs the energy not in a surface but in the volume. That is, something that actually absorbs the energy, but lets little bits of energy that go past and be absorbed a little bit behind it. So what we call this is it is a volumetric heat transfer, heat exchanger. So the idea is to figure out what kind of a working fluid we should use, and what we do essentially is we use a gas which particles in suspension. Okay, what kind of particles? It could be carbon particles, for instance, and if we have carbon particles suspended in a gas in here, the radiation would come in and will meet some of the particles, and when it meets just the gas, it goes past and hits another particle that is further down the direction of the propagation radiation wave. So this is the idea of the design of this kind of system. We call it a participative working fluid. Why participative? Because we say that it absorbs energy in a volumetric way. And as I said, some of the people thought about this before us, and not only for heating up the fluid, but also to make chemical reactor, to put particles in it that not only absorb the energy, sensible heat, but also react chemically to the in the presence of the radiation. Just let me before I leave this this slide, let me give you a little bit more of detail. We have the working fluid in here, and we let it in through a certain point. It goes inside, and then it exits. It goes out from the heat exchanger somewhere. So in this way, this would be a kind of a standard heat exchanger. Working fluid comes in, gets hot in here, and then goes away. But the point is that the absorption is volumetric. Now, if we are talking about a chemical reaction, then in order to make an optimized design for this kind of heat exchanger, we need to have two things. First, we have to reach certain temperature. Second, we have to stay at that temperature for certain time, so that the reactions take place and are more complete. The fuel that goes in gets combusted inside, as we would say in other contexts. So this is the kind of design that we're talking about. And also, we are looking for chemical reactions that are suitable or that are convenient for this for these systems. One of the most important, in my opinion, chemical reactions is the dissociation of zinc oxide, or tin oxide is the proper name in English. I don't know. The idea is as follows. We have the reactor in here, and then we have concentrated solar energy coming inside. Then, if we reach a temperature of 2,300 degrees Kelvin, and we have a supply of tin oxide in here, then when it gets heated up at this temperature, it will dissociate. We will have a powder of tin and oxygen in here. So by putting energy in it, we split the molecule, and we get this combination at this temperature, and we put it in a quench where we separate. The oxygen is going to this place, and the zinc is going to the hydrolyzer. In the hydrolyzer, away from the solar system, in another laboratory, we put the zinc in contact with water, and the zinc gets oxidized, and we get hydrogen out of it. So essentially, what we're doing is we are generating hydrogen with the sun. Okay, so we are constructing a source of hydrogen using the sun as an input, and then the zinc oxide goes back to the reactor. So this is very good, because zinc oxide is kind of a catalyzer, and we are splitting water. Okay, using this strategy. So this is not our idea. Idea has been discussed by Professor Steinfeld in Zurich. And the point is that this has a potential of reaching high energy conversion efficiencies and economic competitiveness. So I would like to slow down a little bit and invite you to reflect on this idea. We put sunshine in, we take hydrogen out. That's it. I mean, sorry, and water. Solar and water, solar energy and water, and we take hydrogen. The idea sounds fantastic. The idea sounds really good because not even the tin oxide is wasted because it comes back. It goes back to the reactor. So we're interested in this problem, and we will see whether we can understand the thermal processes that take place in the reactor. Now, as good scientists, what we do is we idealize the problem. We cannot deal with such a complicated geometry. I'm going to change this geometry for this one. It is not as bad as it looks. I mean, this is more realistic design, and this is very much a mathematician shape of the problem. But we do have the essential ingredients. First of all, we have a container that mimics this container here. Then we have a radiation window. What would be the radiation window that we have in here? And then we have the inlet, which is this one, and the outlet on the other side of the box. Okay, so even though the geometry is different, the important things are incorporated in the model. Also, I want to comment that when we have this situation, when we are heating up this region in here due to the solar beam incidence, we are in presence of gravity. And as you will know from your courses in heat transfer, when we have temperature gradients in presence of body force, we have natural convection, right? So natural convection is a key ingredient of the design of this heat exchanger, because when the participant medium gets heated up, it will start moving due to this temperature gradient, right? So we will have together two main driving forces. First, it will be the forced convection due to the pressure difference between the inlet and the outlet, and the second would be natural convection due to the presence of gravity. So this is the idea. Let's try to see whether we can understand what's going on inside the system. The physical model that I'm going to present to you will include radiation, heat transfer by radiation, by conduction and convection. But unfortunately, I will stop short of discussing turbulence models and chemical reactions. This will be the topic for another PhD student, and you will be very welcome to apply for the position. Okay, I warn you, this is tough work to do, but very interesting. Okay, let me try to explain very briefly what are the main components of radiation heat exchanger. Well, first of all, let me start by a very idealized picture of a radiation beam that comes from left to right.
Okay, so we go from left to right, and we have a gas that is represented by the a yellow field, and particles that are represented by these small balls in here, circles in here. Now, if the radiation comes in a system of this sort, it will be attenuated by absorption. That is, the radiation will interact with the circles and will be absorbed. So if I take balance of the radiation that comes out on this side, it will be attenuated, it will be diminished. Why? Because some energy is stored in the particles. That's one effect. And we have a mathematical model for that, and we say that the beam intensity, that is watts per square meter, is reduced, and the reduction as it moves, and the reduction is proportional to a certain physical property that is called the absorption coefficient. Now, there's another way in which the beam gets scattered, and that is when the radiation interacts with the particles essentially, the surface of the particles will start, the molecules will start moving around, and they will emit some radiation, and this will be the scattering. The scattering, again, the attenuation due to scattering will be a similar effect to that of absorption. The intensity will be, the reduction of the intensity will be proportional to the intensity itself. So the constant of proportionality would be the scattering coefficient. But there are two other effects that are that come into play in here. First, we call it the augmentation or the increase by emission. That is, once the particles absorb energy, they will start re-emitting energy, and part of the energy re-emitted by the energy re-emitted by the particle will be in the direction of the beam. So if we have, let's say, a low energy beam coming in this way, when it starts re-emitting, part of it will go in the same direction, and it will be increased. And also, we will have increase of the energy density due to scattering. The same phenomenon that reduced the intensity of solar energy in here will increase by the following mechanism. Imagine that the energy comes in and interacts with a particle. It will start re-emitting in all directions. But one of the directions will hit another particle, and the other particle will scatter again, and one of these beams will go in the direction that we are analyzing. So, in this sense, we will have another much more complicated phenomenon that has to do with what happens in the whole of the particles that surround these ones. So the increase of energy in this direction due to the scattering of the rest of the system will be an integral of the intensity of the energy. So what we end up with is that the energy that moves in certain direction will be diminished by absorption and by scattering, but increased by emission and input scattering is called this other term. Obviously, we would have to consider what happens to the intensity of the light beam in time, but since this is it has a coefficient that goes like the inverse of the velocity of light, normally we can neglect it. So what happens is that when a beam of light comes in a system that interacts with it, it will be dispersed, but it will be transferred to the another position. So this is the way we can take into account what happens to the light beam that comes in a container that has a participating medium. Okay, I would like to stop here and see whether there are any questions or comments on this. This is very important. Yes, please. Yeah. In here we have a concentration of 18,000 maximum. It has to do in terms of the geometry. Yes, this 80, it's 9 times 9 square meters, and they concentrated in a spot of 7 centimeters in diameter. Exactly. Yeah. Okay.
What is the minimal temperature to get the reaction take place? The minimum.
Yeah, 2,300 degrees Kelvin.
But that is the minimum.
Yep. That's what you need to split the. What you need to split the molecule. That's an endothermic reaction, so which is perfect for our.
So this project is for industrial application. It can be in a.
Well, I wouldn't like to say that it would be for industrial application. Right now, it's just a laboratory application. If it works, it could be scaled up. But for the time being, I wouldn't like to commit myself in saying that it has an industrial application as such. Okay, let's come back to this place, and let me just emphasize that we said that the beam goes in certain direction, right? And in my equation, I use an S. Okay, so this is the direction that a radiation beam goes. But I have to translate it if I want to use this concept. I need to translate it into my Cartesian frame of reference. So what I do is I write the equation in terms of S in this very simple form. I have the change in the intensity of the beam is proportional to an extinction coefficient times the intensity of the beam plus a source term that has to do with the temperature of the system and the scattering effect. Now, as I said, I have to translate it into my X, Y, Z frame of reference, and this is done very simply by geometrical considerations. If I take the projection of the direction with respect to certain specific direction, and I can write the previous equation this one, not in terms of the direction s, but in terms of the Cartesian directions x, 1, 2, and 3, which would be x, y, and z, times certain factors. So I can take into account radiation now in my Cartesian frame of reference. And now I'm ready to start establishing the form of the heat transfer equation. So this is the equation I had before, and if I want to calculate the source of energy that is inside my reactor due to the presence of light radiation, I just take the divergence. I take the divergence of the heat source, and it will be of this form. Essentially, it will be the integral of the intensity, which I assume that I can calculate in here if I integrate this equation. Now, if I know this, then I just plug it in here, and I hope that you are familiar with this equation. The time derivative of temperature plus the convective term is equal to the diffusive term minus the source term. Why is it minus? Because I consider it from the point of view of the system, and so this will be a negative quantity when I take the temperature, when I calculate the temperature of the whole participating medium. I get a source term, a positive term, when it comes when I calculate the temperature. So this is my new heat transfer equation, right? This is what I have to solve. Now, bad news, because I have another unknown, but I have another equation. So in principle, the system is closed, and I can go on. I can calculate. Okay. Now, another feature of this equation is that I have the velocity here. And what is the velocity of the system? I told you that we have two driving effects. First of all is forced convection, for instance, promoted by pressure differences between the inlet and the outlet. Secondly, we have natural convection. So we have to solve for this, and we have no way out but solving Navier-Stokes equations. I'm hoping that you're familiar with Navier-Stokes. Everyone in the room. Okay, fair enough. So Navier-Stokes, as you know, is a momentum balance, which are the usual terms in here, the time dependence and the convective term. Also, I have the pressure gradient and the diffusive term, but I have now to add a force that is a force that has to do with the density of the system, and I'm using this Boussinesq approximation to see to indicate that all properties of the fluid are constant except density, and I'm using an equation of state that indicates that the density is proportional to the temperature gradient. So what I have in here is that I have the temperature plugged in a natural convective term in the Navier-Stokes equation, and as you well know, this in order to solve this, I need an equation for the temperature, which I provided through the energy transfer equation, and also I have to have another equation because I have the pressure, and this is the mass conservation equation. So my system is now closed, and I can integrate. Okay? The point is, how do I integrate? I need numerical tools to integrate the system. Before I established the numerical tools that are the best for this problem. I have to consider the boundary conditions, and the boundary conditions have to do first of all with the radiation beam. I know that the radiation beam has certain value different from 0 at the window where the radiation is input in the system, and all the walls are absorbing, and they are not going to be considered in the thermal balance. So we assume that they absorb the energy, but they don't get heated up. This is to simplify the model. Then we need also boundary conditions for the temperature, and we assume that that boundaries are also thermally insulated. At the window where the beam comes in, we consider that we have, and I'm sorry, this should be a minus sign. We know that the energy that goes out from here can be re-radiated to the atmosphere, or can be lost through a convection in the front side of the system. So now we have boundary conditions, and we have a closed system of differential equations. So what we need now is to establish an integration strategy and a way to visualize the results, which are going to be real tough. Yes? Yes, I was commenting that I'm using the Boussinesq approximation. In the Boussinesq approximation, you consider that all properties of the system, all physical properties of the system, are constant, except the density in the source term. That forces me to use a small temperature gradient. But we have enough problems now to relax this condition. Okay, so what we do is we use a finite volume method. This is not cylindrical, this is Cartesian coordinates. I'm sorry for this mistake. And then we use a projection method to solve the radiation thermal energy. We use a simplex method to uncouple the pressure link. And Manuel, my student, developed this integration code, because we are a little bit reluctant to use the commercial codes, mostly because when you use a commercial code, then you lose track of what you're doing. And we prefer to develop the code ourselves. And this has worked very well with very many students, and now we have a fairly large library of integration codes. Now, the visualization is going to be a big headache, because as you might know now, we need to describe a vector field, three-dimensional vector field that is time dependent. Okay, so we have to be very, we have to have good strategies of visualizing the results. Also, before I go to the results, I would like you to consider this. Imagine that we have a parcel of fluid coming inside the system, right? It will try to move from the inlet to the outlet due to the pressure difference. Okay, that would be the kind of the simplest way. It would go in and then get out. Okay, but we would like to have this parcel of fluid residing inside the system, so that it has better chances to undergo this chemical reaction, right? Now, if we have natural convection, then the parcel would get in and will be driven around by the natural convection flow. So we would like to have something like a spiral orbit of this parcel. Okay, we don't want it to go in and then go out, because it might not be at a correct temperature. Or else, we don't want to have idle regions in the heat exchanger, because if we have certain path of parcels of fluids going from the inlet to the outlet, and some other parts of the volume where the working fluid just moves around in loops, that will be not very good for our purposes. Okay, so we want the whole volume to participate, and we want to establish the geometry of the orbits of the particle pads such that they would go undertake this chemical reaction with a high probability. So that's what we are after. That's what we want to. That's kind of information that we want to extract from this model. So before I show you the results of the numerical integration, let me discuss a very simple model. In this model, what I want to do is I want to try to see whether I can simplify the mathematics in such a way that I can understand them. I have 1 hour and a half, Abel, do I? I want to understand the basic properties of the solution. So let me open up a quick bracket in here so that I can try to explain what happens inside the system. First of all, I will consider a system that is just one-dimensional. Okay? Out of my volume, I will choose just one dimension, from inlet to the outlet. I'm sorry. Secondly, I am going to assume that I know what is the velocity of the system. In this way, I am ignoring natural convection. I'm only considering forced convection, and I know what the velocity is. Okay? Okay, you may say this is stupid because this is not going to reflect reality, and I would partially agree. It is not very good model, but it does capture some important features of the solution. I'm going to consider that constant cross-section and mass conservation would imply that the velocity is constant. So thus the velocity only depends on temperature, on time, would depend on time, but it won't depend on the position. And I'm going to consider an internal heat source, right? What kind of equation would describe this phenomenon? Well, it would be, the heat transfer equation would be the familiar heat transfer equation with time dependence and also a convective term. And I will consider, in principle, a source that is a volumetric for this model and a sink, right? So T is temperature, SO is source, and SI is sink. And the initial condition will be that the temperature inside the system will be T initial, and I will have that T initial will be constant temperature in the whole domain of integration, which will go from 0 to L, to capital L, and I will have a boundary condition that the temperature of the working fluid that comes into the system is constant, is T0. And this becomes an advection equation. Perhaps you're familiar with this kind of equation from your mathematics courses. And if we have a homogeneous equation, that is, if we consider that this side is 0, then we would have a first order wave equation. That is, the distribution of temperature will be carried around in time. Okay? Please think of this in this way. I have a system, and I hit it with an internal source. So this is moving, and this internal source is going to move the hot spot away from the system, right? Now, this is not homogeneous, so this is not just a wave that is going to be moved out. It's a wave that it will be increased in its the temperature will be increased due to this internal source that represents the beam. The internal source that I will use will be an exponential function that has a maximum at the entrance and that will decay as it goes in. So this is very much what would happen in a system that has just absorption, right? So let me try to explain the system again. I have one-dimensional system. Think of a tube in which we have an internal source. The internal source is very strong at the inlet, and the fluid gets heated up at the inlet, but it's moved towards the outlet. Okay, and the source is stronger at the inlet, but it's still different from 0 somewhere inside the tube. So the temperature will go up. And I will not consider a sink for the time being, just because I want to make this simpler. Now, some interesting mathematical properties of this solution is that if the source does not depend on temperature, then the temperature distribution reaches a steady state. And this you can see very easily from here. If this term does not depend on time, remember we don't have this one, then we can look for a solution that is not dependent on time. We ignore this term, and the solution will be very simple. The integration of this term equals something that depends only on x, which can be done easily because u is known. So if the internal source does not depend on x, then the temperature reaches a steady state. That's an interesting property of our system. Why? Because the system gets heated up, but if we wait long enough, then it will reach steady state. Okay? And we will be extracting the heat that is being input through the light beam. The heat will be extracted from the outlet of the system, right? And it is parabolic in x and t, so we have only one condition on each variable. That's not very important in this context. Okay, now let's see what happens to the temperature as function of x as time goes on. And I hope this works. This is what happens. This is temperature, okay? And this is the position inside the heat exchanger. So it starts growing because of the incidence of the light beam, and then it reaches a steady state. Okay? So even though the time keeps the system keeps being heated up by the internal source, the temperature distribution is not changing anymore. Okay? Now, I would like you to look at it again, and you can see the wave that is being dragged towards the out. There you go. We can see the wave being pushed away towards the outlet, and the temperature at the exit, which is proportional to the energy that is being extracted, is going up, right? So we know what is the shape of this curve because we can integrate very easily, and we can see it is essentially a exponential, decreasing exponential function. Well, this is increasing exponential function, right? So now the important thing for us is how much energy can we extract from this system, and this will be proportional to the temperature at the outlet. So let me plot the temperature at the outlet as function of time. That is, how fast does this temperature go from 0 to the maximum value? And this is shown in this picture. We have the temperature at the outlet as function of time. And we see that it starts at TL equals 0. That is, at the beginning, we don't have energy that is being extracted from the system because it hasn't had enough time to heat up, right? But then it goes up, and then it reaches a steady state. And we can actually calculate the value of the steady state, right? We can evaluate the previous expression, not in x, but in L, and we know this value. Mind you, this is just a toy model, just to try to understand what's going on inside our system. Now let's go for the real thing. Let's go for the numerical model, the one that takes into account three-dimensional effects. Okay. Now I'm sorry to say that when we face this kind of descriptions, it is very difficult for us to grasp the physics because of the very complicated system. I'm just formally, I'm just telling you that this what you're going to see has a Reynolds number of 1.3 if we consider the Reynolds number at the inlet. The Rayleigh number that describes the natural convection inside is 10 to the 6, and the Prandtl number is around the Prandtl number corresponding to air. This is just an illustration, it's a sample. We don't claim that this is very realistic, but we want to understand the physics. Okay, first of all, let me show you the equivalent graph of the plot that I showed you last, which is in here. This is the energy coming at the end of the device as function of time, which is proportional to temperature. So we can compare this plot with this one, right? So at the beginning, we see that we are not extracting energy from the system. But then it goes up and then reaches something that looks like a steady state, although it is not exactly a steady state. And why is it not? Mostly because we have the natural convective flow that is moving around the fluid inside. So we don't understand the details, but we do understand the general features of this of the behavior of our system. Now, let me show you what happens at certain very specific spots. I'm going to show you what happens at the beginning, and then what happens somewhere here, and then I'll show you what happens in there, in the inside of the device. This is, I'm sorry, this is very busy, but well, that's the way it is. I'm showing you velocity here, temperature here. This is a vertical cut. These two are horizontal cuts. and this is a vertical cut. Let me try to see whether I can explain myself. The system is almost a cube, and we make a cut in the middle with a vertical plane, so that we see the window. Half of the window is shown, and the other half is blocked by this plane. And the arrows obviously mean the velocity in that plane. And we see that the fluid comes in and starts pushing the fluid that is inside, and the fluid is pushing in the middle but goes around. And this is shown from this picture from above, right? The flow is more intense near the walls, as you can see in here. Okay, this is a cut, a vertical cut that is pushed back, so that you can see what happens near this wall, right? These are temperature fields, and as you can see, the temperature that is near the region when the radiation beam is hitting gets hotter and forms a film of a boundary, thermal boundary layer here, and then it gets dragged, and some instabilities are shown. Okay, so what we are looking at is the details of the motion inside this three-dimensional system. And also, we see very, very clearly the natural convection cells that are formed in a cut, a vertical cut somewhere around here in the middle of the container. This is at the beginning. Then I will show you this. This was what happened here. Now I'm going to show you what happens there. And this is a similar picture, but I want to stress that the flow is not symmetric anymore. So the flow tends to go to one side, and this is a phenomenon that happens often when you have a jet coming in to a system that is wider than the entrance of the beam. Okay, so I'm sorry, I'm not going to describe all the details because it will take me forever, but I just want to emphasize the complexity of the flow. Now I will show you what happens, I believe it's in here, when we are more or less in steady state, and what we see is essentially the same sort of thing, but now the flow goes definitely, well, it goes down here and goes definitely towards one side. This indicates that the hottest region is in here, but the hottest region is very close to the entrance of the cold fluid, so the cold fluid is, or the hot fluid is correctly dragged away from the hot spot. So this system is working the way we want it. Okay? Now, in order to show you the complexity of this motion, I'm going to show you, well, I hope it's going to work. You can hardly see the outline of the box in here. Here's the window, there's the inlet and the outlet, and I'm going to show you isosurfaces of temperature. So the temperature, I can draw a surface with the same temperature, the isosurface of temperature, and I will cut it in the middle so that the outer isosurface don't block the sight of the inner isosurface, right? And I will show you as function of time. Also, I will show you some of the instantaneous streamlines. I wanted to show you the path lines, but unfortunately we didn't finish on time. So this will give you an idea of what would happen to a parcel of fluid that comes in. And again, let me see if it works. Okay, there you go. This is temperature field, and these are the instantaneous streamlines. And you can see some of the spirals that we were looking at. The fluid is coming in and going out, and the action is very much inside this this system. I'm very sorry that this is not polished yet. There are a few things that need to be mended, but nevertheless, it gives you an idea of how complicated the orbits of the fluid would be in the inside of the system. And this is the same plot that we've been discussing, and so at the end of the movie, you would see what would happen, not in a steady state, but in a state that has little changes in time. Okay, now this gave us an idea to try to propose another design of the system in which this natural convection system would be we can make most of the natural convective system. And this is my the last idea is, by understanding what's going on inside the solar energy heat exchanger, we can propose new possible designs that optimize the performance of the system. And this brings me to the final remarks. They are very much what I've been saying. So if you want to read them, and I will only say that we have a lot of work to do, and all students that want to join the effort are very welcome to get included in our working team. Thank you very much.
Thanks, Dr. Eduardo. We're giving it to you, diploma.
Thank you very much.
If you have any questions, please, you can make it in Spanish or in English. There isn't any problem.
Doctor, pues un tema muy interesante. Tengo yo unas preguntas con respecto pues al diseño final. El tiempo para la disociación del óxido de zinc cuando se calienta ese medio, y los dispositivos para dirigir el zinc y el óxido por dos canales diferentes, ¿está considerado en la simulación? ¿O cuáles son los planes para considerarlo en un estudio posterior?
Okay. Can I answer in English so that everyone... the question was how long would it take for the reaction to take place, and the other is how can we separate the two products of the reaction, right? And the idea is that the reaction itself is very, very fast. That's no question about it. Now, what we need to do is to expose the material to the correct thermodynamic conditions, so that we can make it be at the right temperature for the right time, in the sense that the whole thing, for instance, a particle can reach that temperature. Now the particle is very small, so that the time required would be small as well. But we want to put it in the right place. Now, in the usual reactors, what you do is to just put the material in and hope for the best, which sometimes you're lucky, sometimes you're not. we want to know whether we can help in this direction. Now, once they are splitted, they are separated somewhere else. What goes out from the outlet is a mixture. You don't separate the things, in the two components in here. You don't physically separate the components in here, but you split the molecule. That's what, that's what that takes more energy, and that's what solar energy provides. Is the question answered? Okay, thank you.
Thank you. You said you use Boussinesq approximation, but the temperature is above 200 degrees. How do you make sure Boussinesq approximation is still valid at this temperature?
Well, we don't. That's the truth. Now, let me try to explain a little bit. It's not as bad as it looks. The reason is that what we need to, for the Boussinesq approximation, we need to have temperature gradients small. So if we have that the whole thing is at 2000 degrees C, and that it goes to, say, 2010 degrees, then we would be justified to use it. Now, you're perfectly right. In reality, this is not the case, and we should take into account non-Boussinesq effects. This would be this can be kind of a second chapter of this project. There are so many things that are missed, that are put away, that we have to try to simplify the system so that we can gain a little bit of understanding. That's our justification. But you're right. There are very many questions that have not been answered.
First, thank you very much for your conference. I got two questions. The first one is, can you show us the equation of the dynamic model? And the second one is, what was the software that you used?
Not the simple model. The model is comprises the mass conservation, then the momentum conservation, fixed with these conditions, plus the heat transfer conservation, plus the radiation equation. So it is all in all 1, 2, 3, 4 equations, 4 unknowns.
And that equation was introduced to ANSYS?
No. We developed the code ourselves. We don't use commercial codes, because commercial codes are kind of we say in Spanish, espada de dos filos. I don't know how do you translate that into English. Double-edged sword. Thank you very much. The reason is that you get results very easily. You don't know whether they're correct or not. And when you want to make a change, then it's very difficult to understand what you're doing. That's why I would recommend that in a postgraduate school, the students would develop the code themselves. Now, this seems to be a little bit more difficult than it actually is, and but I think that it's worth the effort. Then you can manage. You're the owner of the ball. You can change the way you want.
Thank you.
Hello, good morning. My question is if the results that you are getting with the simplified model show some agreement with the stationary solution or approximated stationary solution of the transient model.
We cannot make a one-to-one comparison for very many reasons. I mean, there are some physical effects that are taken into account in one model that are not in the other one. That's that was not the purpose of the development of the simplified model. What I think is the value of the simplified model is that we can understand the kind of average behavior of the detailed model, and that's about the usefulness of this kind of toy models, they call it in English, the models that just give you a hint of what's going on, but it would be very difficult to compare. When you make a comparison of the qualitative properties and they come out to be the same, something is inside the simple model that should be appreciated, that can be useful for you, but not a one-to-one comparison. It's different things.
Do you think that if you correct the absorption coefficients on the simplified model to make like effective coefficients that also takes in account the effects of the scattering, maybe it could be a good approximation that could be useful when you take the reaction of the system?
Yes, yeah. I think that's a very good idea, very good idea, because you can plug in physical effects in the simple model to see how the general properties of the heat exchanger change. That could be done, and perhaps it would be interesting to see how the, for instance, the steady state distribution of temperature changes. And also that now that you're mentioning that, there's an interesting way to look at the simplified model as well. For instance, you can think of the model as being good for an orbit of partial fluid that enters and then runs and then go out without spiraling or anything. Okay, that would be the best place to apply the simplified model. But if you want to take into account the other motion, what you would do is you would slow down the velocity. You would consider a velocity that is a little bit lower than the one that you would get by just forced convection. And so the residence time would be increased, and perhaps you can extract some interesting information from there. We haven't done that yet.
Okay. ¿En español puede ser?
Sí, claro.
Bueno, al último mostró un diseño de la nueva cámara. ¿Nos podría explicar un poco qué es lo que motivó ese diseño en donde la entrada es vertical? Bueno, obviamente fue basado en los resultados que obtuvo del modelo, pero ¿nos podrían explicar un poco sobre eso?
Okay, the question was why is this ideal quote model better? And we think that this is a better design because the forced convection goes in the same direction as the natural convection. So the two of them will be working together. So if you shine the beam horizontally, and then you put the working fluid moving from the lower part to the upper part, they will be kind of exposed, and they will be subject to natural convection, but natural convection will also be going that way, and they will exit immediately. So if the system is slow enough, it will be something like a rolling band. You will be putting the material, exposing it to correct thermodynamic conditions, and then taking it away. And this will be renewed. So it will be, we think, very efficient. And we're working on the modelization of that design to see whether we're right or not.
There is another. Yes, Dr. Samuel.
Yes. Do you plan or are you running experiments to validate your results?
We are not ourselves, but my colleagues that work in the Renewable Energy Institute are building solar energy receivers of this sort, and we're trying to convince them that our results are correct, and so that they would be motivated to test them. I hope that in future we will be able to report experimental results.
Thank you. Regarding the zinc oxide reaction system, there's some sintering of the particles. The other one is
Century?
yeah. The other one is what kind of inert gas is used in the reactor, and for the whole setup, determine the efficiency, considering, for example, milling of the particles.
Yes, this is a multiple item question. Yes, let's start from the beginning. The particles are suspended in air, so this is kind of free in this sense, and we have not considered the whole the whole bookkeeping, energy bookkeeping of the system, but our colleagues have done, the people in Zurich, and they are pushing forward this idea, but as far as I understand, they are not being supported that much by the Swiss government. And this is bad news and good news. Bad news because they're very good and they were leading the way, and good news because now we can have a possibility of making a big contribution ourselves here in Mexico. So we're working hard.
Last question, Doctor? Last question? Dr. Eduardo, thanks for the conference.
Thank you.